Want to get started?
Loyal.
You're the guys that are actually going to graduate. You came from the
We had a little piece of paper that says
We
passed.
We started the class, pulling the fire alarm to avoid the final, but
Mark on a curve.
you came for the last class. This is where we get the punchline. Wonder what it's all about. Last time when we left off, we had just basically finished up particle physics in only 2 classes, which is quite a feat. Just to remind us where we were, it was really about figuring out what the universe is made out of and the forces that we have in the universe that keep things together, that create matter, the different kinds of exotic particles that you can make out of the fundamental building blocks. So this was the set of fundamental building blocks, and everything is made out of this. What we'll be talking about today is a little bit more of how things work on different scales. Scales of small sizes, of what the actual interactions are, and then scales of fast speeds, which we've talked very little about. But just to finish up some of the ideas here, remind us where we were with the small things, the building blocks. We have these different pieces. The quarks are most of the stuff that you make things out of. Electrons tend to fly around those things. The one that's familiar to us is the electron, which will make an appearance a little bit later today again. That's where we carry electric current, and anything that we interact with is mostly due to electrons. The quarks are what make up the protons and neutrons that we're used to in everyday matter, as well as all these other things, the more exotic particles. And then we have these gauge bosons, which are the particles that carry the force back and forth between things. One of the things we're missing here is anything to do with gravity. These things are very small. They do feel gravity, but gravity is such a weak force compared to the rest of the forces here, compared to weak force, that it doesn't make an appearance in anything when we talk about particle physics. Gravity really has no place in that discussion because it works on such a completely different scale. It also works by a set of completely different rules, and we have not yet figured out how to make the rules that apply to gravity look anything like the rules that apply to particle physics and to the small scale things, the rest of quantum mechanics. And that's one of the big unanswered questions in the human understanding of the universe globally, is how those things can be correlated. How I have 2 totally different systems. There's got to be some way that they're unified at some scale, and we have no real idea of how that happens. We have analogies with what we know, so we assume it must be that there's some kind of a gauge boson that applies to gravity, a graviton. There must be kind of gravity waves that do these things. But in terms of what it really is, or finding them, there's no concept there. So when we talk about gravity today and where that comes from, that overlap, the lack of an overlap is the big open story in pretty much, like I said, human understanding of the universe.
Could you talk for a minute about the Higgs boson, which A seems to straddle the electromagnetic force line, and B, isn't that named after somebody, which violates one of the rules?
It's named after somebody, but it's not named by the guy it's named after. So you can't name, if I discover a particle, I can't name it after myself. But what happened was, with the Higgs boson, I have all these particles, and most of these, except for the photon really, they all have mass. They all have a different mass. And I have to write on here what the mass is. 2.3, 1.27, 173. They're all different masses. Why are they those different masses? Where do those masses come from? It's kind of uncomfortable that I have all these particles, and in my fundamental theory of the universe, I need to, by hand, type in these 16 numbers to be able to describe everything. I should have one number and then be able to say, well, because of this interaction, these interactions give rise to all these other masses. This is where all the masses come from. I can't say that with the regular standard model of particle physics here. So there was the idea that there's this Higgs particle, and I'm simplifying this a bit, but that the Higgs particle creates a field which is what gives rise to the masses of the different particles. And if I do that, then the model gets cleaner, more simple. I need fewer ingredients to build it out. In reality, the Higgs is not quite as globally applicable in terms of what it gives masses to, but that's the right concept for why it was so important to be able to define. So it was postulated that there would be this Higgs particle. It's actually a Higgs field, and the particle would be a manifestation of that field. And that Higgs field is what would give masses. But then we had to go find it. And the idea was, well, it should be about this heavy, and then we looked for it by building a machine big enough to make particles that are that heavy, because my machine has to have enough energy to be able to convert that energy into the mass of the particle. If my energy is too low, I don't have enough energy to turn into mass to make the particle. I can't make a 100-pound particle if I only have 50 pounds of energy coming into the accelerator. So I had to build a bigger accelerator to find it, and it wasn't there. So then I had to build a bigger accelerator. And these accelerators are discovering other new particles and doing other valuable things, but the construction of the Large Hadron Collider, which was the new accelerated machine at CERN, which is the particle physics lab in Switzerland, or under Switzerland, that lab has been around for a long time, done a lot of different things, but that newest, biggest machine, the sort of excuse for building it was to be able to get to an energy where we could find the Higgs particle, where it really, really should be at this point. It was sort of a similar story with the top quark. The top quark, so the bottom is at 4.2 G, and the top is 173. It's by far the heaviest thing, not just by a little bit in terms of the quarks, or really on this table altogether. And even the W's and Z's here, the W's are 80 G, the Z's are 90 G. Doesn't matter what the G is; those are just sort of big numbers, right? So this is 80,000 times. Well, it's 40,000 times the mass of the up quark. Much, much bigger. So the W's and Z's weren't identified, weren't actually created until fairly recently, because we needed a machine big enough to do that. The top quark, which was in the mid-90s, somewhere early mid-90s, the machines had to finally get big enough to be able to make it. Everyone knew it was there because we had these 5, and there's something missing here. It's got to be there somewhere. You can't, physics wouldn't be that weird to not have it. So we looked for it, we could figure out more or less where it was. They finally found it, and it was kind of anticlimactic. It was big parties, but everybody was there anyway. It was more relief than celebration. We found it. The Higgs was sort of a similar story, except we had to get, it was harder to produce, and it's only produced in much messier interactions. So I needed much more complicated detectors to be able to figure it out, to find it. And that's really only in the last couple of years at the LHC that we were able to do it. There was hints of 1 or 2 of them that you might have been able to see at Fermilab, which was the second biggest particle accelerator in the world. It was the biggest for a long time, most powerful. But now it's confirmed at CERN. There's still a variety of other unknown things out here with respect to the Higgs, but at least we can actually now put it here. It's in gold, as Susie pointed out this morning, because it was so expensive to build a machine. We might as well. So those are my building blocks. And the important story here, which is kind of been the theme throughout, continues a little bit today, is what really distinguishes these things is the forces that they feel, which defines the way they interact with each other. The strong force really only applies to the quarks, and the gluon, which carries the strong force back and forth. And that was the story of nuclear fusion. That's why the protons hold together. That's why the nucleus holds together. And the electromagnetic force, that is what we interact with all the time. That is what we feel. That's our daily experience. It's really an electromagnetic force story. Primarily, it's the electrons. These guys are around, but they're much heavier, so we don't encounter them. They're not part of normal matter. The muons are screaming through the room at the moment. You're feeling them go through you, but there's no real impact. The photons are probably certainly the thing we see the most. That's light. Those light particles, that's an important story for the rest of today. The neutrinos are around. The weak force is important for a lot of processes that we have. There's a lot of technology in space on it. Just without the weak force, the world wouldn't really work. But it's not something that we feel or interact with much. It's really what allows these things to change into each other. So there are manifestations of that, but it's not something that we interact with all the time. And the neutrinos, of course, are so light and only weakly interacting. They don't feel any electrical forces. They don't feel the strong forces. And so they pass through you without being noticed. They pass through everything without being noticed. It's very hard to detect them. That's why we build those giant tanks in the mines that we talked about last time. They're filled with the photodetectors, just to be able to see the neutrinos and count them. And the story of the neutrinos, and whether or not they have mass, and the contributions they make to the processes of the universe, are all relatively recently discovered stories. In terms of the fundamental interactions of beta decay and some of those radioactive processes, they were known that they had to be there, but actual experimental detection of them and measurements are really fairly recent. So the last piece of this, I have those things, And I am making, in these particle accelerators, I'm smashing things together as hard as I possibly can to be able to get enough energy to make new particles, to make new things happen. So this was the top quark. Remember, that's the really heavy one that I said was only fairly recently discovered, although everybody knew it had to be there. And I can have a case where I have, in these accelerators, protons going one way, antiprotons going the other way, and I collide them. That's a collider. Any of the really big, high-power things are these colliders. When I do that, instead of throwing something at a target and seeing it spews off the back, I make a gigantic mess. Because I'll make the heaviest particles, but the heavy, heavy particles want to decay very, very quickly. They don't last very long. They don't last long enough really to even see themselves. What you see is what they fall apart into. So I'll create, in this interaction, a top and an anti-top. Or I create these particles with the energy, but I have to have one particle and an anti-particle. It's mirror image pair that are created together. Then those will decay into a bottom and a whole bunch of other stuff, a W, which goes into its own sets of other stuff. All these different particles come off. What I have is just a huge mess of particles that come out. And I have to account for each of those particles, see them all, and figure out what they all are. And derive from that what this interaction is. And there are other things going on here as well, and I have to sort out what I was actually looking for from the rest of the noise. And in the earlier cases, it was easier. We spent a lot of time last week looking at bubble chamber pictures where I see a particle come through and I watch it decay. And I'm looking for a specific interaction, watching something happen that I sort of expect to happen, or looking for something I didn't expect to happen. In the modern case of a collider at high energies, a ton of stuff is happening all the time. I'm collecting all of it, and I have to sort it all out to understand it. So it's a much more complex problem. It's a lot less conceptually clear. I can't look at a picture of it and understand anything. I really have to account for each individual piece. The way I do that is because of the different forces that apply to these different components. I can sort them out based on, it's like a layer of SIDs, or trying to sort out different sizes of a coin sorter. Where I dump all my coins in, and I can sort out the half dollars from the quarters, from the nickels, from the pennies. Those things are just done by size. It's actually a little bit more like a vending machine. When you probably don't realize this, but when you put in your money into a vending machine, it rolls the quarter down to measure the distribution of mass with the quarter, so you can't put it in a washer because the mass distribution will be different, will roll differently. And then there's a magnet sitting in there. It actually runs your coin down a ramp, flies it through the air, passes by a magnet, and falls into the right chute. If you have a slug, or you just get a washer from a hardware store, that's going to be magnetic, and the magnet will pull it the wrong way, and it'll go somewhere else, and that's when it spits back in the change tray. So if you take a quarter and you shove it into the thing, it'll come out through the change tray instead of being registered, because we spin it at the wrong speed there. That's the same kind of technique that we're using here. We just sort all these things out based on the different properties. So it's the fact that I have these different properties, and feel these different forces, that allows us to do that sort. Do you have a question, Chuck?
You talked before about making particles. You're not actually really splitting them out of existing particles. I mean, they're there.
In the early days, we were splitting up existing particles. What we're doing now is taking enough energy, getting enough energy in one place at one time that has this excess energy, and it's going to go somewhere. And it will create particles out of nothing out of the energy. So remember, mass and energy are the same thing. They're completely interchangeable. They're just different ways of looking at energy.
That's why
really.
it makes them always in particle-antiparticle pairs, because energy can turn into a balanced, like the top and the anti-top.
Right, there's certain things that are conserved here. I can't make, for example, if I start with a certain amount of spin, I have to have the same amount of spin afterward. So if I can't make one particle, because it wouldn't conserve momentum, it wouldn't conserve the spin. If I'm talking about making leptons here, I have to conserve lepton number. I need to be able to make these things in pairs, but I am actually just creating them out of the energy. I don't know what I'm going to create. I just have a certain amount of energy, and then I'm allowed to create anything below that amount of energy. So it could be anything as long as it's below that.
Just one other question. Where do you get the antiprotons from? I mean, you assume you get the protons and antiprotons. How do you manufacture antiprotons?
Through the same kinds of interactions at lower energies. Protons are easy to make because they're very light compared to all the rest of the stuff. So I smash a couple of things together with enough energy, and then I sort out which ones are going to be the protons. The easiest thing to make, so I'll have most of them. Or I tune the energy of my collision so I can only make protons, I can't make anything else, or I'll make protons, neutrons. And if I make protons, neutrons, then all I have to do is put it in an electric field. The neutrons have no charge, so they won't go anywhere. the protons that I can pull through and then shoot them this way. Since they're in an electric field and the protons are positive and the antiprotons are negative, the protons are going to go this way and the antiprotons are going to go that way. And once I sort them out in that initial reaction that I create them in, then I can pass them on to the main accelerator ring and then get them circulating. So most accelerators, pretty much all accelerators, have I have a picture here. You'll see more than one ring here. So I've got two. This is a Fermilab in Chicagoland. I have actually in a small area here is where the initial protons and antiprotons are manufactured, but they're shot in a ring to start with to sort them out and get them to a certain energy on this injector accelerator. Then they're injected into this main ring, where I have the two counter-rotating beams that go around. And this is again where I can then split off the beam of protons for my fixed target experiments, where the proton beam shoots out this way, or I can have the proton and antiproton beams cross each other, and then I'll get a certain number of collisions, and where the buildings are here and here are the two main experiments, CDF, the Collider Detector Facility, and D0, which are the major collider experiments there, where I can see everything that spews off. Barbara.
A few questions, if I can keep them all in my head. So you can't, it's not like you can have a canister of protons.
Right.
You have to create them in that first cylinder at the time that you need them and then put them into the other accelerator to do what you need to do. Okay.
Now these things are referred to as storage rings, because I make them. Once I have them, I can just keep spinning around in circles more or less forever, as long as I keep putting energy in to keep them going. So I'll make them, and I'll just keep making them and making them and making them until I get a lot of them in that storage ring. And then I'll decide to start the collisions. I'll open up that valve, essentially, so they can collide and get a lot of collisions at once. Now, I can time that so I'll get bursts of collisions. So I can take a burst, take some data, make another burst, record that, so I don't have a constant set of interactions.
Okay. Next question. Conservation of mass, conservation of energy, they're really the same thing because mass can be converted into energy and the other way.
There's conservation of energy, and mass is just one kind of energy. There's, there's heat, there's, say, light, there's a variety of different kinds of ways things can move. All these things are energy. There's the energy of speed, which is kinetic energy. There's the gravitational energy. If I lift something off, it wants to come together. There's the confinement energy that keeps an atom together, for example. If I break that apart, that releases that energy. All those are different flavors of energy, different ways energy is manifested, but it's all just one big energy. And so I'm free to move back and forth really between any of those different forms. And mass is just one of those different forms.
So the simplistic statement of matter can either be created or destroyed.
You create and destroy matter all the time.
It's not really true, it's actually energy.
Right.
That cannot
Energy
be
is
created
conserved.
or destroyed, and it changes form.
Yes, that's
So
exactly
it
right.
can't be created or destroyed, but it can change form.
Right.
And it can change into matter.
Right. Now there's a quantum mechanical concept which isn't quite true, that you can violate the conservation of energy, but only for a really short amount of time. So you think of that as I can borrow the energy from nowhere, as long as I give it back pretty quickly. It's not strictly true, it makes some people uncomfortable, but that's usually the way that that's also thought.
The last question is, when this happens, when you have the proton, antiprotons colliding,
Right.
is there a noise? Does it make a sound?
It doesn't make a sound, in part, I talk about really, really high energy collisions, I'm talking about really, really tiny things. So it's high energy compared to these infinitesimally small particles. But it's not high energy in terms of any kind of human interaction. You wouldn't feel it if it happened. You look at your hand. The other reason it doesn't make a sound is all sound is a compression of air. There's air around, the molecules in the air, and if they get squeezed together rhythmically, that makes a sound. If I squeeze them together once, that just makes a pop or a pressure wave. So sound is really just a rhythmic wind. In these cases, these particles are small enough, if they hit anything else, we wouldn't be able to keep accelerating them. So everything is done under a vacuum. There is no air there, so there's nothing to carry the sound. It's like being in space.
In your picture, when you saw these protons smashing against each other,
Yes.
you said that Chuck asked that question, is how are the pieces, when they split off there, are they already there, or are we creating them? And you said the energy with which we charge these protons against it creates them.
Yes.
So my question is there depending, if you increase that energy infinitesimally, I mean, to huge numbers, is there a finite number of particles that exist, or can we create almost an unending number of particles depending on how much energy we bang these things against each other?
It's an excellent question, and the answer is sort of both, depending how you look at it. There will be an end, but the end will not be soon. These are the building blocks that we know we have. So if I exclude novel physics, if I say, okay, this is all the universe really has, then I can combine these things in a certain number of ways, several hundred ways, but really just several hundred ways. But even if I have them combined, I can add energy to that and get them into a higher energy state, and that looks to us like a different particle. It has a different mass, it behaves a different way. So even though I have the same, maybe something that's 2 ups and a down, I can make, that's a proton, and if I add more energy into it, it becomes a lambda particle. It's a different, or a delta particle. It's a different particle, but it's made out of the same constituent things. So as I keep adding energy, I can make these higher energy states, even with the same set of subatomic particles, and therefore create more and more particles as I add more and more energy. So that was how all these particles got discovered in the first place. There is likely, you're going to hit a limit where now I've added so much energy that things are going to fly apart, where the lifetimes become so small that they're meaninglessly small. And you can't consider it a particle because they're not bound together anymore. The energy is such that there's too much energy for them to hold together. They decay almost before they're created. The lifetime is 0. So at that point, I've reached another threshold. And the idea there is one of the goals for the very, very high power accelerators. You actually can't do with protons, you need bigger things. Is to create what's called the quark-gluon plasma. In that case, I smash them together, there's so much energy there that I don't have particles. I have a soup that consists of a mess of quarks and a mess of gluons. They're all just one big soup. Nothing is confined into any kind of organized form. It's like I've melted the fundamental stuff of the universe. The reason the quark-gluon plasma is of interest is because that is what the universe was at the very, 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 very beginning. The tiniest fraction of a second after the Big Bang, that's when you had the quark-gluon plasma, and almost instantly that would have separated out as the universe expanded and things dissipated. It started cooling, and you started forming the ability for these things to be made into actual particles. The reason that's also interesting, not just because it's the beginning of the universe, because that is the one and only case where you would be able to get what you can think of as a free quark. It's not really free, it's in this quark-gluon plasma. But the strong force, remember, which is the color, is the charge, the red, green, blue, you can't have something that has color by itself. So you can't have a quark by itself. If I try to take a quark by itself, more quarks will pop out of nowhere just to be able to be friends with it, make sure I have something that is colorless. The quark-gluon plasma is the one case where I have this mess of quarks, and they're not combined in 2 things. You can call the whole soup one big thing. And probably the universe was colorless at the beginning as well. But they are still separate quarks, so that is relevant. Building an accelerator that can do that is not so easy, not on the proton-proton side, so we have it on Long Island. Brookhaven has a lab that accelerates at high energies things that are bigger than protons, small nuclei. Right? Gold on gold is the biggest thing they can do. So instead of having, it's 1,000 times more energy because you have more stuff you're crashing into each other. Okay.
Josh, if you go back to that table,
Yep.
are you guys really waiting for an anti-gluon? But there is a photon with no mass and there is a gluon with no mass. Why do you need a particle anti-gluon?
Everything has its antiparticle. So everything on here has an antiparticle. There are cases, like for the photon, where the antiparticle of the photon is the photon,
Right.
which sounds strange, but mathematically it works.
Conceptually, be that a gluon is a gluon,
Well, this
who needs an anti-gluon?
you need an antigluon. Yeah, everything has an antiparticle. But the antiparticle is allowed to be the same thing if it doesn't have any of the properties that would change. Okay, so the last thing I want to say about this particle physics topic here before we move on to quantum mechanics is how we detect these things. You know, I said you sort it out, like I said, this is what the detector really is like. This is the Collider Detector Facility, Fermilab CDF. I've got protons coming in from one side, antiprotons coming in from the other side, and this large object, the person is probably about this tall here, is several rings of different kinds of detectors and then layers in between them to be able to sort out what's what. So in the very beginning, I have what's called a vertex detector, or a set of the wire chambers that we talked about before, essentially that can track where a particle is going, so I can draw a line back and figure out where the thing started in the first place. Because I have these collisions over a whole region. This could happen here, it could happen here, it could happen here. If I'm going to trace out what really happened and know which particles, which products came out of which collision, I have to know what the vertex was, where they actually crashed. So I have that vertex detector in the middle to give me the basic confines of what happened. And then, as I go through, I have magnets, so I can see what the momentum of the particle is, because something that has a higher momentum will curve less because it's going faster. If it has a small momentum, it will curve more in the magnetic field. Again, that's only if it's charged. So if it doesn't curve, I know it's not charged. And then I have different layers of shielding that will absorb the lighter particles, but not absorb other particles, the heavier ones potentially. So the muons will get through stuff that the electrons won't. That way I can sort out electrons and muons, which otherwise look exactly the same. Then I have calorimeters of different kinds so that I can see how much energy each of these particles have. And once I do that, I can take an event, build the story of that event, essentially reconstruct event by event what happened. I also have, again, on the roof of this entire thing, a set of detectors to make sure that nothing I saw was a cosmic ray that came down. So if I see that, it's a rejection event. I reject the event. And then a set of electronics here that acts as what's called a trigger, which means this is good, I should report it. I meant the basic constituents of what I was looking for. So these different colors here correspond to different layers of the detector, where I have the tracking chamber, which is that vertex detector, tells me what the trajectory of each particle was. A calorimeter for the electrons, where things break apart into little pieces. So as I have this electron or positron come through, it's going to break off into a million little pieces, meaning they'll have enough energy that they decay into other things. And I trap all of those things in the calorimeter, so I make sure I have collect the total energy of whatever that electron had. And I make that thing big enough so that I do capture all that energy. So I have a little detector in between the sandwich that says if something gets through, I've missed some energy and I should account for that in my reconstruction. Heavier things or hadrons, stuff that has quarks in it, actual matter, will pass through that electromagnetic calorimeter, go into the next calorimeter, and then the muon chamber here. If a muon comes through, it will pass through all of this stuff and actually keep going out the back. I'm not going to capture the energy of the muon. But if I detect it on the other side of everything else, I know that's the only thing that could have made it through, that I would still see in the muon counter. If I had a neutrino, that would also go through, but I'm not going to go through everything. I'm not going to detect it at all. It's also not charged. The fact that these are charged allows me to actually see their path later. So these are examples of some of the things that are in there. But obviously, it becomes a very complicated system with many, many layers and details. This is what it looks like in real life. This is the actual detector. The beam comes through this way. It's opened up right now for maintenance or actually reinstallation of some of the internal components. There's a guy in this picture, but if you're in this picture, you'd be about this tall on the ground. It's a huge thing inside this chamber. These are lots of magnets and lots of time from lots of grad students wiring everything together to make it.
So everybody's signature on the top.
Oh yeah, that's right. Yeah, so everybody works on it, gets to sign it. This is part of the story of working in particle physics also. Something on this scale, this runs for, say, a year and a half, 2 years at a time. This is the length of the experiment. So I have to build this thing, which will take about 5 years of actual construction. Probably takes several years, 5 or so years before that of conceptualization. Then you run for a couple of years, and then it can take you several years later to analyze the data that came out of it. So the experience of going through as a graduate student, really going through your career, you'll spend, you'll have a piece of this piece here, or maybe you'll be a specialist in one element there. You have to know enough about everything to analyze the data, but you'll spend years working on your piece. It goes together, you go to the lab, and for your year, you spend at the lab working 1 to 8 hour shifts, and you'll be assigned a certain number of shifts during usually the night if you're a grad student. Watching for red lights flashing, because you may or may not know what they even mean. Record the data, and then go home and do the analysis of all of this. So you're part of the big experiment. It takes, CDF had probably 400 scientists working overall on the program. The smaller one, K-10, we talked about last time, the fixed target experiments, which is what Susie worked on.